Hello. Today we are going to compute the Lagrangian for a particle in circular motion. So given by these coordinates, x equals r cosine theta and y equals r sine theta, where r is the radius. So assuming that theta varies with time, we can compute the velocities simply by taking the time derivative. So we get the x component velocity is going to equal r dot cosine theta minus r theta dot sine theta. Simply using the product rule for derivatives. And similarly, we get y dot is equal to r dot sine theta, and we add r theta dot cosine theta. So we know kinetic energy is a half mv squared, so therefore we want our velocity squared. So we know that v squared is going to equal x dot squared plus y dot squared. So what's this going to equal? This will equal simply our x dot components and our y dot components all squared. So we're going to get r dot cosine theta minus r theta dot sine theta all squared, and then to that we add r dot sine theta plus r theta dot cosine theta. And we square that as well. Right, so what's this going to equal? So all we need to do is expand the brackets. We do that times that plus that times that, and so on. So if we do that, we're going to get theta dot squared r squared multiplied by sine squared of theta, and then we minus 2 theta dot r dot sine theta times the cosine of theta. And then to that we add r dot squared cosine squared of theta, and we add theta dot squared r squared cosine squared theta. And then finally to that we simply minus 2 theta dot r dot sine theta cosine of theta. And then we add final term, which is r dot squared sine squared of theta, like so. So we can factor out a couple of things here. So the first thing we're going to factor out, it would make sense to anyway, is to factor out a theta dot squared. So this is still v squared, so v squared is going to equal theta dot squared. So where's theta dot squared here? We've got theta dot squared here, I've got theta dot squared here, so therefore we get r squared sine squared theta. And then to that we add r squared cosine squared theta. Let's factor out a minus 2 theta dots because we have it in that equation and that one. So we do minus 2 theta dot going into r dot sine theta cosine theta, and then we do minus r dot sine theta cosine theta, which you can see will cancel out. And then we add, let's factor out an r dot squared, because we have it in that equation and we have it in that equation there. So factor out an r dot squared, we get cosine squared theta plus sine squared theta. Right. So, what does this become? This is equal to, well, our theta dot squared. We can factor out an r squared here, can't we? So this would be theta dot squared multiplied by r squared multiplied by sine squared theta plus cosine squared theta. Okay? And then we add simply r dot squared, because look here, they cancel out, so that becomes a 0. 0 times minus 2 theta dot is just 0. And we can cancel this down to a 1, because cosine squared theta plus sine squared theta is 1. So therefore, all we need to do is add an r dot squared on the end, like so. Okay? So sine squared theta plus cosine squared theta is simply 1. So therefore, our velocity squared is going to equal theta dot squared times r squared plus r dot squared. Okay, now it's very easy to compute our Lagrangian. Our Lagrangian is simply going to be our kinetic energy plus minus our potential energy. So therefore, our Lagrangian is going to equal m over 2, okay, half mv squared for kinetic energy, multiplied by our velocity squared, which is simply theta dot squared r squared plus r dot squared. This is all in polar coordinates, okay? And of course we add our potential energy, which is a function of our radius. Okay, and there is the Lagrangian in polar coordinates for a particle in circular motion or in a circular orbit. So I'm sure you'll be able to use the Euler-Lagrange equation to compute the momentum and so forth. In fact, I'm going to set that as a little challenge. I want you to derive our angular momentum and show that it's conserved. Okay, so that's what I want you to do. So I'm sure that made sense, especially this expansion we had here. That took a while, but you can see that it all boils down to a nice simple Lagrangian. Okay, so I'll see you in the next video.